and welcome to today's CSAIL Forum. This is our platform for rigorous intellectual exchanges that are at the frontiers of computer science and artificial intelligence. Today, I am delighted to introduce my colleague, Yoon Kim, who will speak about efficient and expressive architectures for language modeling. So I'd like to welcome all of you to be engaged participants. Please start by putting your name and your location in the chat so that we know who is attending. And please put your questions in the chat. At the end of the presentation, we will have an opportunity to do Q&A with the speaker. And with this, I will pass it over to Yoon. Yoon, please take it away.
Thank you for the introductions. Great. I'll get started. Thank you for the introductions, Daniela. My name is Yoon Kim. I'm very happy to be here, and today I'll be telling you about some efficient and some recent sort of body of work, not necessarily from my lab, but from the community on efficient and expressive architectures for language modeling. So before getting into the technical details, I think it's worth stepping back and sort of like reviewing the current AI research program. And I think the high level overview goes something like this. So we have some data, some model with learnable parameters, and an optimization objective. Now, in the case of modern large language models, the data is given by, without an exaggeration, a civilization's worth of text. The model is given by a transformer architecture, we'll talk about, and the objective is to actually have the transformer tweak its parameters to give high likelihood to the training data. And this is the maximum likelihood objective. And in some sense, in a real sense, all you're doing is compression, i.e. maximum likelihood is minimizing the code length of your training data using the model parameters. Now, what is the purpose of this? Of course, it isn't necessarily that we want to compress the data itself, but the hope is with the right model, the model will be able to capture sort of the underlying intelligences that produce the data, which is given by sort of external world, and then in the case of language models, humans, so intelligences sort of deploying and using language that produce the data. And there's sort of several additions to this recipe. Maybe we can think of this as the language model pre-training stage. And once we have the model, we can now have the model execute actions in the world, get verifications, generate its own data, and then compress that using the weighted likelihood objective. And, I'm being hand wavy here, and maybe that's roughly reinforcement learning. And then once you have the model, you can use it in various ways and to do useful things. And this is, in modern large language models, sometimes called test time scaling. So this is maybe the current AI recipe. And I think the argument, the view that I'm going to espouse in this talk is that this model architecture really is a crucial ingredient in this modern AI recipe. And as maybe one evidence of this, I think it's worth looking back into large language models back in 2007. So this is a very well-known paper from Google, and the title of this paper, which came out in 2007, is Large Language Models and Machine Translation. And if you look at the abstract, we see they're actually training pretty big language models. So they're training a n-gram-based language model with 300 billion n-grams. That's equivalent to 300 billion parameters. And they're training this model on 2 trillion tokens. So even by today's standards, these are quite large language models. And the only thing that's different is what the model is. So in the data, just like in today's language models, we have trillions of words. And the optimization objective is the same. It's the maximum likelihood objective. Of course, in these lookup table n-gram-based language models, the maximum likelihood objective is given by counting and dividing n-grams, whereas in today's transformers, the optimization objective is solved by using something like stochastic gradient descent. But it is pretty remarkable that we basically had the same recipe from a high-level standpoint, but due to the differences in architecture, I mean, 2007 we had improvements in machine translation from large language model, but no one was, talking about ChatGPT or AGI. But applying the same objective to today's architectures, we're getting some very useful systems like ChatGPT. So I think this is maybe one evidence that within this AI recipe, having the architecture right is an important component. So today's language models are based on largely what's called a transformer architecture. So how do transformer-based large language models work? Well, basically, language models are next word prediction systems. So here I'm representing the language model as a neural network. It gets in a input text like MIT is located in. It produces an output piece of text, output word, and this gets fed as input. And the combined input gets fed into the LLM again to produce the next word. What does this architecture look like? This architecture, by and large, modern LLMs use the transformer network. And what the transformer network does at a high level, we'll get into the lower level details in a few slides, but at a high level, what it does is it gets the input, it represents each word as a vector. So deep learning models operate over vector representations. So it represents each word as a vector, and then it has what's called an attention mechanism, which uses the current representation of the word and performs a pairwise interaction between all the previous words to get a new representation of the current word. And then it uses this representation to predict the next word. And then again, you feed what you've predicted as input, and then this process continues. And with this mechanism, you can sort of produce infinite text given any context. But the key point that's different from previous neural network architectures is this attention mechanism. Okay, and this is really the salient difference between transformers and other types of neural network architectures that many people were using, like convolutional networks or recurrent neural networks. And to the point where the original paper that introduced the transformer architecture had the very sort of like fun title, "Attention is all you need." So this attention mechanism is again the key. And this paper, which was released in 2018, has been incredibly influential. And the transformer network has been found to be quite effective for many other domains other than just language. Now, what are some issues with transformer networks? So they are very accurate and they're an important primitive. So the attention mechanism is an important primitive for accurate sequence modeling. There are several issues. One is that transformers have difficulty modeling long sequences. So I described how, at an intuitive level, the attention mechanism is performing these pairwise comparisons. And we can see these pairwise comparisons, if you're doing this at every time step, how it can get incredibly expensive as the sequence length grows. And we do want sequence models. We do want large language models that can process long sequences, right? So we want models that can process entire series of books. And ideally, we want models that can process sequence lengths in other domains that can be, millions or even hundreds of millions of elements of long. But attention is just inefficient at modeling long sequences because of this pairwise interaction mechanism. Another difficulty that transformers with attention have is they're impoverished with regard to being able to model certain phenomena. So one version of this is state tracking. So state tracking is, in this case, a synthetic task where one version of this is a synthetic task where you might have a bunch of boxes like this, and the box has certain states, like box 1 containing a book, box 2 containing an apple, so on and so forth. And then you have a bunch of permutations of the boxes. So you swap box 1 and 3, you swap box 2 and 5, so on and so forth. And at the end, you ask, where is the apple? So it turns out you can show that this type of state tracking problem, i.e. tracking permutations over a number of states, is actually hard from a formal standpoint. So from a complexity theory standpoint. And this is unideal, right? Because these types of state tracking problems, it's quite toy in this case, but there are, I think, capabilities underlying these types of state tracking problems are real world capabilities that we want in our LLMs, especially when it comes to, for example, having them produce code, right? So in code, you're doing a bunch of variable swaps, and we ideally do want LLMs to be able to track them. So the purpose, I think what I'll talk about this talk is on some recent developments, again, from a community of researchers that suggest an alternative to transformers that can maintain the accuracy and scalability of transformers while being more efficient and more expressive. Before I get into this, I think it's worth going into a little bit sort of technical details about how transformers work. So transformers take in a set of vectors, here denoted from x1 to x5, and produces another set of vectors where the set of vectors has been contextualized against one another. So transformer is a function that does this. A transformer is composed of transformer blocks. So modern large language models might have tens or even hundreds of such transformer blocks. Each transformer block consists of a attention layer, which does these pairwise comparisons that I talked about a few slides back, followed by a feed-forward layer. Again, the real difference of the transformer architecture versus other types of architectures is this attention layer, and this is the sort of the portion of the transformer that we're going to be focusing on in this talk. More review about how attention works. So how does this attention mechanism work? Attention mechanism itself is a set-to-set function, which gets in a vector, in this case of length L by D. Here, L is the sequence length. So here, L is 5 in this example, and D is the hidden state dimension, which in this case is 3. So attention takes in a vector, set of vectors, in this case you can represent it as a matrix, produces another matrix O. What are the computations in attention? First, you use the key query value matrices, key query value projections to get the key query value matrices for each input embedding. And then you use the key query matrix followed by a mask to get an attention matrix. And this attention matrix is an L by L matrix, where L is again the sequence length. And then you use this attention matrix to get a convex combination of the value vectors to get the output. And this is how the attention mechanism works. So this reduces an output matrix O that is L by D, given an input matrix L by D. And here the learnable parameters of the attention layer are these WQ, WK, and WV matrices. And then, of course, this is just a single layer of attention, and this is the layer that I'm going to focus on, but you should think of the other components of the transformer being there as well. So that we're going to have feed-forward layers, we're going to have attention layers elsewhere, but we're just going to be focusing on how there are new sort of primitives that might be able to replace these attention layers. Now, what's good about attention? So so when I explained the attention, nowhere in the sort of the number of matmos that I mentioned did I mention the sequence length. So in particular, the number of matmos that you're doing is independent of sequence length. So certainly the size of the matmol is like, of course, a function of sequence length, but the number of matmos that you're doing is independent of sequence length. And what this means is that attention computation can be parallelized across time. So you can compute attention for all time steps with a single, or sort of like in this case, a number of matmos that is not a function of the sequence length. And this is great because we know how to do such matmos efficiently. And there's an entire industry of GPUs and TPUs and other types of chips for doing this very efficiently. So this is great because that means we can have very hardware efficient training. Another thing that's good about attention, and that's different from other types of sequence models such as convolutional networks or recurrent neural networks, is that attention allows for more direct access into previous elements. And I'm being sort of hand wavy here, but we can sort of see how for this representation to attend to the representation 5 steps back, there is a direct attention mechanism that enables this. So attention from here to there you can just have it assign high weights. Whereas if one were to sort of have this representation be aware of the representation 5 steps back, this would have to be mediated through these types of intermediate hidden states in an RNN. So this is one sort of modeling advantage of attention. Cool. And this is important because I think these types of the ability to look back into context that you have is an important capability that we want in our large language models. Now, what are some things that are not so good about attention? So even though attention can be parallelized, so again, that means the number of matmoles is independent of sequence length, the complexity of attention, the size of the problem, does grow with sequence length, and in particular, it grows quadratically with sequence length. And this means that this means that you just cannot apply exact attention to sequence lengths, on the order of tens of millions. So we've been able to be very clever about structuring attention computations in a way so that you could do exact attention over elements, sequence lengths of maybe on the order of hundreds of thousands or even million plus. But going beyond that is just very difficult because of this fundamental quadratic dependent on sequence length of attention. Another inefficiency comes when it comes to inference. So how do transformers work during inference? We're doing word by word inference. And that means that to produce the next token, we first have the key query value vectors for the current token. And then you use the current query vector with the previous key vectors to get an attention distribution, to get the output vector, and that's fed to the future layers of the transformers to get the next output y, and this is fed as input. And because attention requires attending to everything that's occurred in the past, that means during inference, you need to keep around what's called a key value or a KV cache. And this memory crucially grows linearly with respect to the number of elements in the past, because you have to, for each time step, attend over all previous words. And what this means is that as you generate longer and longer sequences, inference becomes slow. In particular, you're having to move this KV cache that grows linearly back and forth between on-chip and off-chip memory, which can get very slow because memory bandwidth is limited on modern hardware. So these are some of the inefficiencies of attention. And as mentioned previously, transformers with attention without chain of thought have certain sort of they're impoverished when it comes to being able to model certain types of phenomena. In particular, they're in what's called TC0 complexity class. And that means they just aren't able to solve certain types of state tracking problems, in particular the types of problem where I talked about before, where you're swapping, where you have, let's say, permutations over 5 boxes, and you have to decide where the apple is after a bunch of permutations. Okay, so these are maybe some of the things that are not so good about attention. And again, for the rest of the talk, I'll talk about sort of like a potentially a new primitive that can maintain these benefits of attention while being more efficient and expressive. And I'm going to argue maybe variants of linear transformers offer a potential solution to these problems while maintaining some of the benefits of attention. Now, what are linear transformers? So linear transformers or linear attention transformers are a particular type of transformer that was proposed a few years ago. And it's quite simple. So it's a much simpler version of the attention mechanism that we've seen. So in the softmax, the classic attention mechanism, we again have the key query matrix after which you apply the softmax to get an attention distribution that you apply to the value matrix to get the output. So that's during parallel training. During inference, the output at time step t is given by a convex combination of all the previous value vectors. linear attention tells us to do something quite simple. So it just tells us, why don't we just remove the softmax? Okay, so linear attention looks very much like softmax attention, but we don't have the softmax here in the parallel form, and we don't have these exponentials and the normalizer in the recurrent version of the equation. Now, from this, maybe it's not clear we've done anything interesting, but I'm going to argue that this actually does something quite interesting. So in particular, let's look at this equation for obtaining the output at time step t during inference. Okay, so we have the output step at time step t. That's now a linear combination of the previous value vectors. So it's no longer a convex combination, but it's just a linear combination where the weights are given by a dot product of the current query vector and the previous key vectors. Now, because we no longer have this exponential here, we can take the query vector for the current time step outside the summation. And what this means is now we can represent the inner summation as a fixed dimensional matrix that's size d by d. So we're going to call this S here. And what that means is we can decompose linear transformers into the following, where we have a matrix S of t that's updated by an outer product of the current key and value vectors, and the current output is given by applying a query vector on this hidden state matrix S of t. So what does this look like in diagrams? So here we have the key query value vectors. You use the current key and value vectors to get this matrix SFT, and then you apply the query vector on this on this SFT matrix to get the output. And what's sort of key about this is now what I've told you is like linear transformers are basically they're an RNN, but unlike ordinary RNNs, which have vector-valued hidden states, like in LSTMs and GRU, linear transformers employ matrix-valued hidden states. And what this means is that they inherit the efficiency benefits of RNNs, right? So in this case, we no longer need to keep around the key value vector for the previous time steps. All that is represented, or all of that is compressed into this hidden state matrix SFT, and that's all you need to keep around. So this means that we can have, as in ordinary RNNs, linear compute and constant memory sequence modeling. Now, modern versions of linear transformers have some additional bells and whistles. In particular, they use a gating matrix, G of t, or gating scalar, G, that modulates the previous hidden state before the current key, the outer product of the current key value vectors are added. And we can sort of think of this, make the analogy to similar data-dependent gating mechanisms in classic LSTMs and GRUs. And it turns out these gated linear transformers are roughly equivalent to modern state space models. So there have been a lot of really nice work on state space models like Mamba and Mamba2. And it turns out these sort of like, depending on how you parameterize these gating matrix, these are basically the same thing. Okay, so these are modern gated linear transformers, and I think insofar as they're RNNs, I'm going to argue that maybe this lets us get around some inefficiencies of modern transformers. In particular, now we have a sequence model that has linear compute complexity and constant memory complexity, unlike transformers, which have quadratic compute complexity and linear memory complexity with respect to sequence length. Now, how do we actually train this? So because we now have a linear RNN, we can actually train these efficiently. I won't get into the details, but the basic intuition as follows. So here's a pure RNN view. And in this case, when you're thinking about training classical LSTMs, it's difficult to parallelize the computation across sequence length, and that means it's difficult to have hardware-efficient training on modern hardware. But because we have sort of these linear updates or associative updates, we can now reparameterize this RNN as a chunk level RNN, and we can perform the computations in chunk. So in particular, we can have these chunk level hidden states, and we can propagate the information from previous chunks. And then to get the output, you can, for this chunk, let's say, the second chunk, we can use the current chunk's query matrix and interact this with the previous chunk hidden state to get the contribution from the previous, all the previous history. And then we can have sort of like more classic attention and this is linear attention, to get the contribution from the current chunk. And again, I won't get into details, but this means that we can parallelize across time. We can parallelize linear transformers across time. And in fact, we can now have a sub-quadratic parallel algorithm for training that can leverage the computational resources of modern hardware. Now, what about expressivity? Again, linear transformers, even it turns out even gated linear transformers or state space models are still in this complexity class TC0, and therefore they're unable to model certain types of phenomena like state tracking over five or more states, even if the gating function is data dependent. Here's a very nice figure from paper by Will Merrill, where they have a toy version of this problem, and they train various models on this. And as the sequence length grows, we can see how the minimum number of layers to solve this task grows for a transformer, as well as state space models like S4 and Mamba. Now, it turns out nonlinear RNNs, shown in blue here, can solve this with a single layer. But nonlinear RNNs, because of the nonlinearities, they're not parallelizable across sequence length, at least not as easily, which means it's difficult to train them efficiently on modern hardware. But so in this paper, they give a very interesting version of a linear transformer with a sort of a different transition matrix. And they call this IDS4, where this is a linear RNN, a linear transformer, with a particular parameterization of the transition matrix. And they show that this theoretically allows the model to go beyond this TC0 complexity class. And empirically, it is able to solve this synthetic task in a single layer. Now, what does this more flexible transition matrix look like? It basically looks like follows. So whereas previously with the gated linear transformers or state space models, we had a sort of an element-wise gating matrix or the gating scalar. Now we have a matrix multiplication as the transition function, and this matrix is data dependent. Now, what does this matrix look like? So there has been various works that work with different types of these structured map models. So there's a work called DeltaNet, where the matrix is given by an identity plus rank 1 matrix. There are recent works that propose alternatives, but they roughly look like so identity or diagonal plus some low rank component. And it turns out, sort of empirically, so this paper, which used a product of identity plus rank 1 matrices as this transition matrix, it turns out this does allow these types of recurrent models to solve these state tracking tasks much better than transformers. And very interestingly, in this recent work called RWK7, which employs a diagonal plus sort of different matrix, rank 1 matrix, they theoretically show that this type of transition function allows a model to go beyond the TC0 complexity class and solve an NC1 complete problem. Of course, this is contingent upon sort of NC1 being not equal to TC0, which is an open problem. Cool. It turns out we have now linear transformers with these structured transition matrices that can go beyond transformers, at least when it comes to state tracking. And I'm going to argue like we've done something quite interesting and cool with this class of models. So in particular, recall that linear attention and linear transformers, they were motivated from the perspective of having better efficiency, right? So that's why we got rid of the softmax function, which made it possible to reformulate this in RNN. But it turns out if we sort of massage the data-dependent transition function a bit more, we now get a class of models that's still as efficient, but I mean, still more efficient than transformers, but have better expressivity. Now, of course, nothing's for free, so we lose something. So in particular, let's look at sort of how these models may or may not be good with respect to certain capabilities that transformers have. Um, so uh, one way to measure this is called associative recall. Um, and a motivation for this is like given by looking at natural language sentences and noticing that when a model's processing or modeling sort of natural language, we reuse a lot of sort of, let's say, entities or a lot of words or entities that occurred in the past. So in this case, Hakuna Matata, it occurred in the past, and it'd be nice to be able to sort of attend or look back into such context to produce sort of the next word, Matana, given Hakuna, for example. And uh, this is a paper from Simran Arora, where they did very nice analysis where they showed that a lot of the perplexity gap between such RNN or convolutional models and ordinary transformers is due to the fact that for these types of words where you can predict it, if you could look back exactly into the past, um, these types of RNN models and convolutional models are just not as good as transformers that have this sort of flexible attention mechanism to attend over the previous past. Now, it turns out some of the recent models that I talked about, like DeltaNet or gated DeltaNet, with these types of structured matmos as a transition matrix, are better at these types of associative recall tasks. So here, this is a synthetic diagnostic task, again from Simran, where the key point is you have an arbitrary set of key and values and a bunch of queries, and you need to predict the value associated with the queries. And on this synthetic task, certainly these types of linear RNNs with more flexible structured transitions do better. But this is actually a fundamental limitation of recurrent models. So one of the fundamental limitations that these types of even like more flexible models can't get around is the ability to do recall over arbitrary context. And intuitively, this makes sense, right? So if you have like n bits of information, to actually remember this, you can't compress that into a memory that's constant with respect to n. So I've mentioned how these types of more flexible linear transformers are more expressive than transformers when it comes to being able to do straight tracking, but they're also more impoverished. They're still impoverished when it comes to being able to do arbitrary recall. So how do we get around this? I think maybe one non-answer, but that seems to work well empirically, is just use hybrid models. So what do I mean by hybrid models? Well, insofar as these types of transformers, deep networks with multiple layers, you can use maybe some of these more efficient layers for most of the layers. But for a couple of layers, you can still make use of these full softmax extension mechanism that allows you to, again, do associative recall over arbitrary context. Now, what this means is that from a complexity standpoint, you still have a model that requires quadratic compute and linear memory. But because you're not doing this for every layer, things will still be much more efficient. Um, as an example, highlighting the effectiveness of this strategy, we had some work where we were training not the biggest models, 1.3B models on 100 billion tokens, and we found this hybrid strategy to work really well. So here we have perplexity evaluation on some NLP tasks, as well as these types of recall intensive tasks. And what was surprising was like delta net linear transformers. So these are linear transformers with a particularly flexible structured transition matrix. They do well, but they don't do as well as transformers when it comes to these types of recall intensive tasks. But as soon as you add these types, a couple of global attention layers, it does better in terms of both perplexity and retrieval. So this was at a much smaller scale. Recent work has shown that this hybrid strategy works quite well. So there's a very interesting paper called Jamba, which interleaved Mamba layers with these types of full attention layers, and it turns out they perform better than sort of just using Mamba layers or just using attention layers. Cool. To summarize, we've seen how linear transformers, or I've argued linear transformers, are potentially an efficient and expressive architectural alternative to transformers. but they also still have limitations when it comes to certain phenomena that we want, that capabilities that we want in our LLMs, like associative recall, right? We do want models to be able to attend over code bases of like hundreds of thousands of tokens, and for that maybe an appealing middle ground is to still make use of global attention layers but not at every layer. One thought I have is, like, when it comes to really exploring the long-range capabilities of linear transformers, I think maybe language is not the best domain in which to explore such architectures because, we can do a lot of things by attending over tens of thousands or hundreds of thousands of tokens, but when it comes to modalities like speech and video, I think the quadratic complexity of ordinary attention does really play a factor, and I think maybe those are the domains where we really want to stretch we really want to explore the capabilities of these RNN-like linear transformers. And just stepping back, I think when the transformer architecture was introduced in 2017-18, in some sense, it was great because we now had this general purpose architecture that could model lots of different domains well enough, and all we had to do was compute scale the data and the model size, and that strategy did get us to the current point. But I think there's now a lot of exciting work coming from various groups on like proposing these types of alternative architectures to transformers, and I think this is an exciting time to do architecture research. And with that, I'll end here and take any questions.
That was really awesome. Thank you so much, Yoon. We're excited to see these more efficient models. And so let me start with a few of my questions. I wonder if you have identified any tasks where the linear transformer alternative you developed underperforms as compared to transformers.
Yeah, so when it comes to being able to retrieve uh, things from context, like for example, in the synthetic case, you're given arbitrary key values and then an arbitrary query, and you need to output the value associated with that query. These linear transformers still underperform classic transformers, and I think these types of um, recall abilities are capabilities that we want in real world language models insofar as they're important for things like processing code. And these are still sort of like, like capabilities that linear transformers don't have or aren't as good versus ordinary transformers. And I think this is like a theoretical limitation. And intuitively, if you have sort of an arbitrary length context that you're compressing into a fixed dimensional vector, no matter, as long as the vector is sort of fixed dimensional and not a function of input size, then you can't do arbitrary encall unless there's some structure in the context that you give. Which motivates these types of sort of middle ground strategies like hybrid models.
So for our industry friends in this session, can you give us an example of a specific application domain where you would recommend the use of linear transformers and a specific application domain where you would recommend a regular transformer?
Yeah, so I think modalities where the deployment has to be really fast and the sequence length is really long. So these are modalities like real-time speech processing or long video generation. These types of models, linear transformers, are quite promising, and there has been some exciting work applying some of these types of models to speech and video modeling domains. And those, I think that's also like very practical in that, if you have uh, a million frames, it's just very, very slow and maybe even impossible to do full attention over. Now, when it comes to language and doing reasoning, I do think these are domains where I'm being hand wavy here, but you want to attend and reason over all the context that you give it. And I think that's why especially when you're doing sort of like processing language, you do kind of always want these types of global attention layers somewhere at least.
Oh. So you mentioned videos and other types of signals. I wonder if you can say something about how the language uh, angle of the linear transformer extends to other data modalities?
Yeah, so I think speech and video is one natural extension where the sequence lengths are just much longer than language. Other domains like biology, I don't know much, but I get the sense, for example, DNA can be in the billions of input length, and maybe there are exciting applications to be opened up
Have you
by.
tried some of these multimodal applications, multimodal
We
context?
haven't, but there's been the community, some research groups have, and there's been interesting results applying these models to these types of other.
So is the focus then on speech or on video or what?
People have done speech, video, and DNA as well.
All right, so I'm going to ask you a few more questions and
Yep.
then I will open for broader discussion with everyone in the session. So let's see. I wonder if you can talk about the trade-offs between your method and traditional transformers in terms of training stability and other properties, like, maybe generalization, out of distribution, things like that.
Yep. So when it comes to training speed, if the sequence length gets longer, like in this, so if each batch is over a sequence of, let's say, over 10,000, these models are quite a bit more efficient than regular attention. Now, when it comes to maybe like 1,000 length sequences, 2,000, the speed benefits not as salient. Stability-wise, we haven't found these models to be particularly more difficult to train than regular transformers, although there are stability, training stability issues associated with training regular transformers when you get to a certain size. And what was the second question? Sorry.
So let's see. So just the question was about trade-offs
Yeah.
between linear transformers and transformers with respect to stability and generalization, and any other properties you might want to highlight.
Yeah, and then when it comes to generalization, we've actually I think some of these hybrid models have been able to generalize along certain dimensions better than regular transformers, and we don't really have a good understanding of why, other than non-answers like, maybe these layers are capturing different types of phenomena, so you're sort of having an ensembling effect by making use of hybrid models. Now, pure linear transformers versus ordinary transformers on language tasks, pure linear transformers still do underperform uh, ordinary transformers on just language only tasks.
So let's see, please put your hand up if you'd like to address your question directly to Yoon. Otherwise, I see that there are a few questions in the chat, but I will come to you in just a second. I do have one last question. Can you talk about uh, what kind of performance you observed for tasks that require spatiotemporal correlations?
We haven't investigated those tasks, though we are currently investigating applications of these models to time series data, but we don't have. This is just at the beginning.
So it's ongoing work.
Yes.
Okay, so I have a few questions in the chat. Let's see, Mike Stonebreaker asks, if the domain is structured data, say data warehouses, do you think any of this stuff will work well?
Um, that's a good question, and I think when we say domain is structured data, like data warehouses, that itself is like still a big class of types of different data. But for example, if it's like structured data where an input of this data is, very long unstructured text, I think some of these methods may be promising from an efficiency standpoint.
Okay, Mike, do you want to follow up or should we go to the next question? Okay, maybe we go to the next question from Danielle Pace, who asks, if you have two clinical nodes and want to extract what is new in the second one, which architecture, regular transformers or linear transformers, would be the best? In a sense, you are tracking states. So I wonder if the linear transformers would be more efficient.
Yeah, that's a great question. I think maybe from a theoretical standpoint, you might argue some of these more expressive linear transformers with particular, data-dependent structured matrices might perform better. I will say from a practical modeling standpoint, for these types of tasks, you want to use existing pre-trained models, so you don't want to be training these models from scratch. Um, and by and large, these existing pre-trained models still make use of just sort of global attention layers at every layer, which may change over the next few years. But insofar as you're going to be using these off-the-shelf models, I think you'll be restricted to using these types of global attention layers. Now, there's been an interesting line of work on whether you can take a pre-trained softmax attention transformer, of which there are many, in existence, because every sort of pre-trained LLM is pretty much using this still global attention layers, and seeing whether you can fine-tune them into some of these more efficient architectures. And that may be possible, but that's very much sort of ongoing research.
Awesome. Okay, Rudong Wu is asking with KV cache for autoregressive models, the inference complexity remains empirically closer to OVN within quite a few tokens. Do you think state space models have certain advantages beyond that? And if so, where is the boundary?
Yeah, so that's a great question. So insofar as, like compute is cheap relative to memory movement, and insofar as deployment is memory bound, the compute complexity is maybe not the bottleneck with KV cache unless you get to sequence lengths on the order of millions. But still, you are paying a lot for moving the KV cache back and forth from off-chip memory to on-chip memory. And these models, insofar as you have a fixed dimensional representation within an entire context, the size of the data that you're moving back and forth, that's going to be independent of sequence length, and that's going to be practically much faster. And you do see practical gains as you get to sequence lengths, over a couple of thousand with these types of models. Yeah, which is like a one of the reasons why these models are attractive for things like real-time speech processing.
So I don't see any hands in my little icons. Please put your virtual hand up if you would like to ask a question directly. In the meantime, we have a few more questions in the chat. And so Sebastian Eresheim is asking, have you had a look into XLSTMs complexity-wise, and do you know how they compare to linear transformers?
Yeah, great question. So XLSTMs make use of these linear transformer layers. So you can roughly think of XLSTMs as having some of these linear transformer layers, the in particular gated linear transformer layers, and then having ordinary LSTM layers and interleaving both. Um, I don't think there's been a close comparison at scale of these different types of architectures. One thing that's nice about XLSTMs is insofar as they're still making use of classic LSTMs, they are able to model, have like the expressivity benefits that you get from nonlinear RNNs. Now, this is good from a model expressivity standpoint, but bad from a efficient training standpoint, because as soon as you have these nonlinear LSTM layers, then it's very difficult to parallelize across sequence length, which is crucial for efficient training at scale.
Great, thank you, Yoon. Next question from Jennifer Sunu. Has there been metadata collection upfront at time of input collection or metadata assessment coupled with associated recall mixed into the layers that have been used to help increase efficiency and reduce the number of layers needed? For example, metadata like what language or subject or common keywords the input is related to.
Yeah, that's a great question. So in practice, when you're using these types of models to do retrieval over documents, it is helpful to append such metadata about the document so we can more easily sort of use that metadata to reason or retrieve relevant portions. I'll say there hasn't been like a study of whether, for example, being able to do this allows you to make use of smaller or more efficient architectures. But in general, when you're doing retrieval or retrieval augmented generation, it is helpful to attach such metadata to retrieve documents to help the model do better in context recall.
Great, thank you, Yoon. Okay, next question from Young Sung Chung. In the experiment of the last few slides, Yang et al. 2024, why linear transformer plus 2 times softmax layer is even better than the original transformer at retrieval?
That's a great question, and we don't know why. And it's possible, like a lot of this is maybe this is within standard error, but it is curious that like insofar as transformers are really good at this associative recall, why interleaving these just a couple of them along with these types of linear transformer layers does better. We don't have a good answer.
How might you investigate that?
Yeah, I think maybe one is to really make sure the differences are salient. So have do this over maybe like a more targeted synthetic task. Um, Another thing is I didn't go into the detail in the talk, but you can the delta net linear transformer that I talked about, which has this um, structured map-ball transition matrix. There's a view of that type of linear transformer as actually doing associative recall over a vector space. And this is related to like some stuff from the 90s and 80s on like fast weight programming and associative memory from Paul Smolensky. And from that perspective, I think there is something to be said about these delta net transformers having better inductive biases for associative recall. But still, it's surprising that, that combined with global attention layers, which is actually even more aligned to doing associative recall, um, combining both does better. That's quite still surprising.
Well, maybe we can find some collaborations
Yes.
to explore these questions. Okay, one more question in the chat from Isaac Sanchez. Do linear transformers or hybrid models have any implications for interpretability?
That's a great question. So I would say like model interpretability is hard in general. My sense is these types of linear transformer or hybrid models make it even more difficult. And one reason is like with these softmax attention layers, although it's not perfect, but you could sort of peer into the attention mechanism and see the distributions over tokens and maybe try to, see what's going on. And I think attention, to an extent, is a somewhat human readable human readable output of the internal computations of a neural network. And that's because these models are normalized, the attention is normalized to be distributions. Now, in linear transformers, you no longer have that, right? So you no longer have the softmax, you no longer have a distribution over the previous elements, you just have dot products, and it's unclear whether we can interpret them as easily as we have in attention. Now, there is some work on getting an attention matrix out of these some of more complex linear transformers, and it's possible to do this. And I, I think actually that might be one window into like why these models are computing different things versus ordinary transformers. But I'll say to answer the original question, maybe some of these linear transformer or hybrid models are more difficult to interpret than regular transformers.
Awesome. Yoon, thank you very much for a very interesting and stimulating presentation. I'd like to thank all of you in the virtual session for great questions and for very nice engagement at the end of the talk. And see you all in 2 weeks. Next week, we are hosting our industry partners as part of the CSAIL annual meeting. So please join us in person for our CSAIL Alliance's annual meeting. And otherwise, see you in 2 weeks for the CSAIL Forum. Thank you all for joining us. Thank you, Yoon.
Thank you.
Bye-bye.